Salam sejahtera and salam keluarga Malaysia, everyone. My name is Wesley from the Department of Occupational Safety and Health, a department under the Ministry of Human Resource. In 2020, I completed my PhD in Mechanical Engineering from Tohoku University. It all started in April 2016 when I was informed that my application for MEC scholarship was accepted. Before moving on to the nitty-gritty part of my presentation, I'd like to welcome everyone. Please sit back and enjoy my presentation. I hope you will find it useful. My presentation is about the development of extremely high deposition efficiency of robust and super hydrophobic fluoropolymer coating by cold spray technology and its bonding strength improvement. Let's begin with the important keywords that will be introduced throughout the presentation. The silver tsunami refers to the aging population or senior citizen of 60-year-old and above. 4IR is the acronym for the Fourth Industrial Revolution as stated in our National Fourth Industrial Revolution policy. Now, the next one is difficult. Cold spray refers to the solid state deposition at low temperature without melting. Meanwhile, additive manufacturing is 3D printing. Polytetrafluoroethylene or PTFE is a fluoropolymer classified as a high-performance polymer. Last but not least, a bond coat refers to an intermediate layer between two different layers which act as a medium to adhere the two materials together. Moving on to the next slide, let us see what kind of key technologies were used in my journey to develop a polymer metal integration system and key sector that can be integrated in the future to leverage on the use of these technologies as promoted in our national 4IR policy. The four key technologies are automation and robotics, advanced material, biotechnology, and the currently trending 3D printing. Every key technology is integrated and commonly associated with material fabrication or processing. The integration of polymer and metal using these key technologies is extremely useful to produce functional layers or coatings in biomedically engineered products, especially in the healthcare sector, a key sector. Certainly, it will be critical for our nation to excel in healthcare sector as we are on the cusp of becoming an aging nation. On the next slide, I will share where we stand compared to our neighbor in terms of the aging population statistics and what we should expect from the inevitable silver tsunami, which set the important background or backbone of the research. According to United Nations, Malaysia will be an aging nation by 2030, with 10% or more of our population being senior citizens of 60-year-old or older. Our nation's dependency ratio on them increased to 16.7, as well as the economic dependency ratio of 17.5, albeit lower than our neighbor Singapore. It's still an alarming figure which demands attention from everyone, especially the financial experts and policymakers. Dasar Warga Emas Negara was introduced by the Ministry of Women, Family and Community Development to ensure that affordable and holistic healthcare services are accessible to every senior citizen. With the increasing aging population, government expenditure on medicine and healthcare will also escalate substantially. Age-related degenerative diseases such as rheumatoid arthritis, joint problems, and hips fracture will be more common. The demand for prostheses will increase substantially, therefore inflating the cost borne by the government. This would severely bleed the nation's coffer dry in the long run. Therefore, coming up with an innovative solution from a cheaper and more durable product is timely. But first, we must address the problem revolving around the hip prosthesis fabrication costs. The problem with polymer acetabular liner between the femoral cup and acetabular cup on a hip prosthesis is the persistent friction, resulting in substantial wear and tear, which more frequent than not leads to severe infection that requires an immediate replacement. The cost of replacement increases gradually, as well as the cost to fabricate the hip prosthesis itself. In other words, the fabrication of the liner and femoral head is performed separately, thus increasing the number of parts and eventually the total cost involved. Once we have addressed the problems, now we move on to the research aim. Therefore, the aim is to focus on the development of a scalable and safe way to additively manufacture polymer on metal in a single piece to reduce the cost. To ensure the polymer withstands the test of longevity, a high-performance polymer or PTFE, which exhibits attractive properties for a prosthesis, was used in the polymer metal integration system in the cold spray additive manufacturing process, or CSAM. With a high-performance polymer like PTFE, we expect the layer to be durable, chemically inert, highly biocompatible with human body, and last but not least, high mechanical strength. In other words, CSAM is set to focus on the fabrication of a structurally and functionally sound polymer metal integration system at a reasonable cost with high efficiency. To achieve the ultimate goal, the conventional technique was improvised by introducing the novel bond coat, never before reported by any research groups. To talk more on the novel bond coat and the methodology, let's move on to the next slide. The methodology is simplified on the slide. Like any other material-based experimental setup, the step begins with material preparation. Here, the spray micro-sized powders were prepared. Then, the next step is the cold spraying process. Powders are sprayed on solid surface at low temperature to avoid the detrimental effect of the temperature on the solid surface and the powder. The experimental data are then analyzed. Here, the deposition efficiency is measured as the ratio of deposited powder weight to the used powder weight. Finally, the coating characterization, where the properties of the resulting coating are analyzed. If you are interested to know further, please check out my peer-reviewed journal paper or send me an email if you don't mind. The breakthrough of my research came after years of struggling with weak adhesion and low deposition efficiency, reported throughout the academic journals. Using the low oxide metallic bond coat, it was possible to deposit PTFE on any metal surface for as long as the bond coat was present. The obvious difference can be seen in the short video on the left, taken by a high-speed cam in comparison to the footage taken by a normal video cam on the right. Without the bond coat, the micro-sized polymer particles rebound against the hard surface, leaving no deposition, but on the contrary, plenty of polymer deposition, white in color, is evident for the bond coat sample on the right. The process was assisted by a robot arm to ensure a smooth movement and a desirable outcome. Depending on the traverse spray speed, the thickness of the polymer can be manipulated. as shown in the result, a thick and dense layer can be obtained with high deposition efficiency as much as 95%. To put into perspective, 100% deposition efficiency means no polymer particles are wasted during the spraying process, and theoretically, no rebound particles can be found in this case. The resulting layers of polymer or PTFE on its surface shows very strong hydrophobicity or tendency to repel any water droplets. By repelling the droplets, the surface can clean itself from clinging debris, even with the mere presence of a tiny droplet. From these findings, it was obvious that the invented bond coat layer played a very crucial role in polymer metal integration by cold spray additive manufacturing. In fact, a few international additive manufacturing companies have shown interest in obtaining the bond coat rights and the polymer preparation process to be used in the energy utility sector, defense sector, and many more. To see the impact it has on the international academic field, including the industry in Japan, I will share what my research team and I had gained as a team domestically and internationally. Firstly, we managed to submit an official patent application through the university body. The patent opens up the potential for commercialization of polymer metal cold spray in the additive manufacturing technology, an important key technology in 4IR. Firstly, we managed to submit an official patent application through an official technology licensing organization acknowledged by both Japan's Ministry of Education, Culture and Science and Ministry of Economy, Trade and Industry. I am one of the co-inventor holding about 30% of the rights. The patent application was submitted at early stage of research after the finding. The patent opens up the potential for commercialization of polymer metal cold spray in the additive manufacturing technology, an important key technology in 4IR. At the moment, an energy utility company named Tohoku EPCO, which runs the electricity business in the northeast region of Japan, which, similar to our TNB, decided to collaborate in form of patent sharing practice. As a result, tests using the polymer metal integrated system are being conducted at two sites, one at a nuclear power plant in Miyagi Prefecture, another one at a geothermal power plant in Iwate Prefecture. These tests are being supervised by my PhD supervisor and the company's representative. The details of the prototype testing are shown on the slides. Although we have yet to test the findings on a hip prosthesis, I believe the time will come sooner than expected. I hope my research findings will find their purpose in helping the scientific community to build a better world. Secondly, we won one international award from the Chinese government in the 15th Challenge Cup under the One Belt, One Road or OBOR initiative in Shanghai. Thirdly, we won an award from the Society of Intelligent Nanomaterial from Waseda University, and last but not least, a prestigious award from the Dean of the School of Engineering of Tohoku University for my PhD work, which highlights the pinnacle of my study. The implications of my research on our society, business, and government can be summarized as follows. Firstly, it will improve the public quality of life through the availability of quality products at reasonable price. Secondly, it promotes a sustainable environment by reducing carbon footprints through the fast, scalable, and safe fabrication method using CSAM. Thirdly, it offers competitive and innovative business opportunities at a global scale, as additive manufacturing is becoming inevitably important across the globe. Last but not least, it reduces medically related expenditure borne by the government and helps to focus on prudent spending. After more than 10 years in Japan, living as a Malaysian student in the Japanese community, there were stark differences on how we manage our R&D. My hope to all the policymakers out there are summarized on the slide. Firstly, the government through MITI to give tax incentive to bring in this technology and its application in niche sectors such as Health Ministry and Defense Ministry. Last but not least, the government through the Ministry of Higher Education to provide conducive R&D environment, especially research funding to boost the level of innovation and competitiveness amongst research institutions, including patent registration. Moving on to the final slide, I would like to acknowledge relevant organizations and individuals that have been inspirational throughout my PhD journey. Thank you for bearing with me. Salam Keluarga Malaysia and have a great day, everyone. Thank you.